Hey there, tech enthusiasts! Today, we're diving into the fascinating world of embedded systems. Imagine tiny computers, tucked away in your phone, your car, even your coffee maker. These systems rely on something called embedded C, a programming language that helps them function. At the core of these systems lies their memory. Think of it as the workspace where all the action happens. Just like we need space to organize our tools and materials, embedded systems need memory to store their instructions, the code, and the data they work with. Now here's the catch. Embedded systems often have very limited memory. It's like trying to fit a whole workshop into your backpack. That's why efficient memory management is crucial. We need to make sure our code uses this precious resource wisely. Without proper memory management, our embedded systems can run into serious trouble. Imagine your code crashing because it ran out of memory, or worse, behaving erratically because it accessed the wrong memory location. That's why mastering memory management is key to building reliable and efficient embedded systems. Let's talk about the different ways our code can use memory. This is like choosing the right container for your stuff. We have two main options: static and dynamic memory allocation. Static allocation is like having dedicated shelves for your tools. You know exactly how much space you have, and it's always there for you. In our code, we use static allocation for variables and data structures that have a fixed size and are needed throughout the program's execution. Dynamic allocation is more flexible. Imagine having a magical bag that expands to fit whatever you put in it. This is useful when we don't know the exact size of data until our program is running. We use a special function called malloc, short for memory allocation, to grab chunks of memory from a pool called the heap. But just like with that magical bag, we need to be careful not to overfill it, and we need to remember to return the memory when we're done with it using the free function. Choosing between static and dynamic allocation depends on our needs. Static allocation is great for predictable data, while dynamic allocation offers flexibility for data that might change in size. Pointers and arrays are essential tools for working with memory in embedded C. Think of pointers as street addresses for data in memory. They tell us where a specific piece of information is located. We can use pointers to directly access and manipulate data, which is super helpful for efficiency. Arrays, on the other hand, are like organized rows of containers, each holding a piece of data of the same type. Imagine a muffin tin, where each cup can hold one muffin. We use arrays to store collections of data, like a list of sensor readings or characters in a string. Pointers and arrays often work together. We can use a pointer to point to the beginning of an array, and then easily access each element in the array using pointer arithmetic. It's like having a map that not only shows you the starting point, but also guides you to each house on the street. Understanding pointers and arrays is crucial for efficient memory management. They give us the power to organize and access data effectively, which is essential for writing fast and optimized embedded C code. In the world of embedded systems, every byte of memory is precious. Remember that limited space backpack? We need to be smart about how we use it. Let's explore some tips for writing memory-efficient code. First, choose data types wisely. Using smaller data types like char instead of int when possible can save valuable memory space. It's like choosing a smaller box for a smaller item. Next, reuse variables. Instead of declaring new variables unnecessarily, see if you can reuse existing ones. It's like using the same container for different but compatible items. Also, avoid memory fragmentation. Fragmentation happens when memory gets divided into small, unusable chunks. It's like trying to fit oddly shaped objects into your backpack, leaving wasted space. We can minimize fragmentation by allocating and deallocating memory carefully. Finally, optimize data structures. Choose the most efficient data structures for your needs. Using a linked list might be more memory-friendly than an array for certain tasks. It's like choosing the right storage container based on what you want to store. By following these tips, we can squeeze the most out of our limited memory and keep our embedded systems running smoothly. It's all about being mindful of our resource constraints and making smart coding decisions. Even with the best intentions, memory management can be tricky. Two common pitfalls that can trip up even experienced embedded C programmers are memory leaks and buffer overflows. Imagine turning on the faucet and, forgetting to turn it off. That's a memory leak? It happens when we allocate memory dynamically but forget to free it when we're done. Over time, this can lead to our program running out of memory, causing it to crash or behave unpredictably. Buffer overflows are like trying to stuff too many clothes into a suitcase. It occurs when we try to write more data into a buffer, a fixed-size memory area, than it can hold. This can overwrite adjacent memory locations, corrupting data and potentially causing our program to crash or even creating security vulnerabilities. To avoid these memory mishaps, we need to be vigilant. Always free dynamically allocated memory when it's no longer needed. And, be extra careful when working with buffers, making sure to stay within their boundaries. In the real world, things don't always happen in a predictable order. Imagine your embedded system is controlling a robot. The robot needs to be able to react to unexpected events, like avoiding an obstacle or responding to a sensor reading. This is where interrupts come in. Interrupts are like having a special phone line that can interrupt your program's normal flow at any time. They allow the embedded system to respond quickly to external events without constantly checking for them. Here's how it works. When an event occurs, like a button press or a timer reaching a certain value, it triggers an interrupt. The processor stops what it's doing, saves its current state, and jumps to a specific piece of code called an interrupt service routine, or ISR. The ISR handles the event and then returns control back to the main program, which continues from where it left off. Interrupts are crucial for real-time systems where timely responses are critical. They allow embedded systems to be more responsive and efficient by handling events as they happen. Interrupt service routines, or ISRs, are like the reflexes of your embedded system. They need to be fast and efficient to handle events promptly. So, let's see how to write a basic ISR. First, we need to tell the processor which function to execute when an interrupt occurs. This is called attaching the ISR to the interrupt. Then, we write the ISR code. ISRs typically perform a specific task related to the interrupt, such as reading sensor data, updating a timer, or toggling an LED. It's important to keep ISRs short and sweet to avoid delaying the main program for too long. Once the ISR is done with its task, it signals to the processor that it's finished by clearing the interrupt flag, like lowering a flag to indicate the event has been handled. The processor then resumes the main program from where it left off. Writing efficient ISRs is crucial for responsive embedded systems. They ensure that critical events are handled promptly, allowing our devices to react to the real world in a timely manner. Imagine your embedded system is juggling multiple tasks at once. It's like throwing multiple balls in the air and trying to catch them all. So, what happens when multiple interrupts occur simultaneously? This is where interrupt priorities come into play. Just like in a busy office where some calls are more urgent than others, interrupts can be assigned different priority levels. Higher priority interrupts take precedence over lower priority ones. If a higher priority interrupt occurs while a lower priority ISR is running, the processor will pause the lower priority ISR, execute the higher priority ISR, and then return to finish the lower priority one. Managing multiple interrupts can be tricky, but it's essential for ensuring that critical events are always handled promptly. By understanding interrupt priorities and using techniques like nested interrupts, we can create robust embedded systems that can gracefully handle even the most demanding situations. We've explored the fascinating worlds of memory management and interrupts, two fundamental concepts in embedded C programming. Now, let's bring it all together and see how they work in harmony to create reliable and efficient embedded systems. Imagine you're building a heart rate monitor. The device needs to constantly sample data from a sensor, process it, and display it to the user. Efficient memory management ensures that the system has enough space to store the sensor readings, perform calculations, and update the display. Interrupts allow the device to respond to real-time events, such as a sudden change in heart rate, without missing a beat. By mastering both memory management and interrupts, we empower ourselves to create sophisticated, embedded systems that can tackle complex tasks while remaining reliable and responsive. It's like conducting an orchestra, where each instrument plays its part harmoniously to create a beautiful symphony of technology. As you continue your embedded systems journey, remember that practice makes perfect. Experiment with different memory allocation techniques. Explore various interrupt handling mechanisms, and don't be afraid to make mistakes. The more you code, debug, and refine your skills, the more confident you'll become in building amazing embedded systems that can make a real difference in the world.